Welcome to solverfy.
Okay, so for this problem, you have this circular part of the loop that is rotating connected to another part. And it's all in the presence of a magnetic field, which is into the page. Well, it's not particularly important. And you're told that this circular part of radius A is rotating, and you're asked to find the frequency and amplitude of the EMF induced in the loop. So again, we'll go to our favorite Faraday's law. So minus the induced EMF is minus the time derivative of BA cosine theta, where theta is the angle between the magnetic field and an area vector, which is perpendicular to the plane of this loop. So that could, let's just say that's coming out of the page. And the theta is the angle between A and B. So then what is actually dependent on time? We need to figure that out before we can evaluate a time derivative. B and A definitely don't depend on time. But the cosine of the angle between them does. And so that's going to be, so we're going to need to evaluate the time derivative of the cosine of the angle. And then that angle between the area vector and the magnetic field varies as omega t, so then it's cosine omega t. And if we take that derivative, then we'll get an omega out here. And I'm just going to put magnitudes, not worry about the negatives. So then we have B A omega sine omega t. So let's think about area. We're almost there, right? Because the amplitude is just this. So what do we mean by area? So the area of just this thing? It's tempting to think so. It was tempting to think so for me initially, because I was like, well, we don't even know the area of the rest of it. But let's actually prove that that's true. So the area of this whole thing could be thought of as like the area of the, so the area total is the area of the round. Area of the round plus the area of the rectangular. So the area of the rectangular part, its area vector does not change at all with respect to time, relative to the b vector. So this area vector is not changing its angle with respect to b. Therefore, we can cut it. And then so we can say that when we're referring to, this angle changing, it's just the angle changing for the round part. So only that area is going to contribute. And then that area is pi times r squared, all divided by 2. And so that's B A omega. Oh, didn't mean to do that. B A omega. And then this A is pi r squared over 2. And then omega is 2 pi f. And we're given f, so I'll go ahead and put that in the given section. 40 revs per second. And then omega is 2 pi f, so generally, and so we put a 2 pi f here to get that amplitude. And then therefore we can say that the amplitude, which is this coefficient of sine omega t, is when I calculated it, I got 0.00032 volts. And then the frequency is the same frequency of the driving mechanical rotation, and that's just 40 revs per second or 40 hertz. And I'll go ahead and circle these.